The movement of planets is a fundamental aspect of astrophysics, rooted in classical mechanics and modern physics. Understanding planetary motion involves exploring gravitational forces, inertia, and the laws of motion as formulated by Sir Isaac Newton and later refined by Albert Einstein's theory of general relativity. This detailed exploration will cover the historical perspectives, Newtonian mechanics, general relativity, practical observations, and complex interactions influencing planetary motion. Ancient civilizations, including the Greeks, Egyptians believed in a geocentric model where Earth was at the center of the universe. This model, endorsed by Ptolemy, depicted planets moving in complex paths called epicycles, with his moving along larger circles around the Earth. Despite its initial success in explaining planetary positions, the geocentric model became increasingly convoluted and inaccurate over time, failing to explain observed phenomena such as retrograde motion and variations in planetary brightness. Heliocentric Model. In the 16th century, Nicholas Copernicus proposed a heliocentric model, positioning the Sun at the center of the universe with planets, including Earth, orbiting around it. This model simplified the understanding of planetary motions and provided a more accurate framework. Kepler's laws of planetary motion. Johannes Kepler, using the precise observational data of Tycho Brahe, formulated 3 laws of planetary motion. 1. Elliptical orbits. Planets move in elliptical orbits with the Sun at one focus. This replaced the need for epicycles and better matched observational data. 2. Equal areas. A line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time, indicating that planets move faster when closer to the Sun and slower when farther away. 3. Harmonic law. The square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit, establishing a precise mathematical relationship between a planet's distance from the Sun and its orbital period. 2. Newtonian mechanics. First law, inertia an object remains at rest or in uniform motion unless acted upon by an external force. This explains why planets continue in their orbits unless influenced by another force. The second law, F equals ma, the force acting on an object is equal to the mass of the object times its acceleration. This law helps calculate the gravitational force between celestial bodies and their resultant acceleration. Third law, action-reaction. For every action, there is an equal and opposite reaction. This law explains the mutual gravitational attraction between planets and the Sun. Telescopic observations. Early telescopes, such as those used by Galileo, provided critical observations that supported the heliocentric model. Modern telescopes continue to refine our measurements of planetary positions and motions. Instruments like the Hubble Space Telescope offer unparalleled precision and clarity, allowing detailed study of distant planets and their motions. Space missions like the Voyager probes, Mars rovers, and various orbiters provide direct measurements of planetary environments, gravitational fields, and orbital characteristics. Gravitational interactions. Planets and moons can enter orbital resonances where their orbital periods are simple ratios of each other. These resonances can stabilize or destabilize their orbits. Examples include the resonance between Neptune and Pluto, regions in space where the gravitational forces of two large bodies, such as the Earth and the Moon, create a stable environment for smaller objects. These points are crucial for understanding orbital mechanics and positioning satellites. 5. Perturbations. Gravitational perturbations from other planets, moons, and even passing stars can cause small changes in a planet's orbit. Over long timescales, these perturbations can lead to significant orbital shifts. Factors like solar radiation pressure, the Yarkovsky effect, force due to anisotropic thermal emission, and relativistic corrections also influence planetary motion. The movement of planets is a complex interplay of gravitational forces, inertia, and the principles of motion. From the initial geocentric models to the heliocentric view, and through the precise laws formulated by Kepler and Newton and refined by Einstein's theory of general relativity, our understanding has evolved significantly. The study of planetary motion not only illuminates the workings of our solar system, but also provides insights into the dynamics of exoplanetary systems and the broader universe.